All right, class, so this is an ALEKS topic that's called Calculating Standard Reaction-Free Energy from Standard Reduction Potentials. And this tells us use the standard reaction potentials from the ALEKS data tab, so just clicking right here, to calculate the standard reaction-free energy for the following redox reactions. So this is relating delta G to the reduction or reaction potential, E naught. So the equation that we're going to use for this is delta G equals minus NF E naught. And this is, again, an equation that's on your final exam equation sheet. And we're going to need to utilize it. So the whole thing that we're asked to do in this problem is basically to calculate E from this given redox reaction and then apply that information to solve for this delta G. So the first thing that I would do is I would write out half reactions for my two species, for what's being oxidized and what's being reduced. And when you look at something like this, it looks a little confusing, but it's easy to sort of pick out similar things. So the thing that I'm going to pick out is this zinc 2 plus and zinc. So I'm going to write that out first. Zinc 2 plus, 5 zinc 2 plus 10 electrons is going to go to 5 zinc solid. So I'm writing plus 10 electrons on this side because I know that to go from zinc 2 plus to zinc solid, I'm going to need to gain some electrons. So this would be my reduction. This would be my reaction that's happening at the cathode. And if I've got 5 zinc 2 plus and I want to go to 5 zinc solid, well, each one of those is going to take 2 electrons. So 2 times 5 is simply 10. So I need 10 electrons to do that. So then I'm going to sort of take whatever's left over. So I've got 2 Mn2 plus aqueous plus 8 H2O liquid goes to 2 MnO4 minus plus 16 H plus, and then I'm going to add in 10 electrons on this side as well, right? So if I gain 10 electrons here, those 10 electrons have to come from somewhere. They have to come from my other oxidation reduction half reaction. So this is all the rest of the pieces, and I'll write plus 10 electrons there. Then what I want to do is I want to use this ALEKS data tab, or if you have this table, you can just use this table as well. And I'm going to look for these different things. And right here, I'm finding my MnO4 minus. So again, remember that these are all written as reductions. So for this one, which is written as an oxidation, it's going to be the reverse. So I'm going to be looking for MnO4 minus plus H plus. So here I see MnO4 minus plus H plus. So let's see if we can highlight that. MnO4 minus plus H plus 5 electrons. So really what I have here is double what I have on my equation sheet here. But that's okay. If I double my coefficients, my E naught stays the same, so don't need to worry about that. Goes to Mn2 plus 4 H2O, and I've got 8 H2O. So again, it's just doubling. So this is telling me that for this reaction, so as this reaction is written as an oxidation, the E naught for this reaction would be minus this, minus 1.51. It would be the opposite because I'm flipping it around. So for this reaction, E naught equals minus 1.51. And I'll do the same thing for this zinc reaction. And again, since this zinc reaction, I've got 5 zinc 2 plus goes to 10 electrons plus 5 zinc solid. I'm just going to be looking for zinc 2 plus essentially. So way down here at the bottom, I've got zinc 2 plus 2 electrons goes to zinc solid. And if I multiply all of this by 5, right, then I get to my 5 zinc plus 10 electrons. So this would be minus 0.76. I don't need to change this at all because this is as it's written, so minus 0.76. So E naught equals minus 0.76. So if I add these two together, I'm just going to add these two potentials together. So then for this reaction, the E naught is going to actually be minus 2.27. So this E naught is a minus 2.27. So this is not a good reaction. It's not a good cell. It would not be spontaneous. It would be one way to sort of think about this. We're going to be looking for positive E values for reactions that will be spontaneous, for redox reactions that will be spontaneous as they're written. So this would be not good. The opposite would actually be good, but for this problem, we can still do it for this problem. So now I'm ready to apply this delta G reaction. So what this reaction is telling me is that if I take minus N, so N is going to be the number of electrons again, so in this case that's going to be a 10, the number of electrons that's moving back and forth in the balanced chemical equation. So that's going to be a 10. Faraday's constant is 96,500. And then my E will be minus 2.27. So if I do this calculation, I get a value of, where'd it go? 2.19 times 10 to the 6th. So this is a very big delta G value, and this would be units of joules. So if you follow your units here for Faraday's constant and everything, you get units of joules with this calculation. So that would be 2.19 times 10 to the 3rd kilojoules. This is asking for our answer in kilojoules. That's why I've changed it there. So this is a very big positive delta G. That should indicate to us positive delta G, non-spontaneous, that is consistent with having a negative E value. And that's it for this problem. This is the answer that we're looking for here. So just one equation that we need to apply. We need to, there's sort of 4 pieces to this equation. We can figure out essentially 3 of them and solve for the last one. I'm solving this E potential from my standard state potentials. You can use this ALEKS data tab, or you can use this chart here. Even though I've got 5 zinc 2+ plus 10 electrons, I'm just going to be looking for the simplest version of this, and then it doesn't change my potential. As long as the coefficients, are consistent, it's really okay. If these are 5s and over here it's 1s, that's not going to change my potential. It's just sort of, the rule for these potentials. I'm going to add these together. So once I have my 2 half reactions, I'm going to add them together to get my standard state cell, and then just apply that to my delta G equation. And that's pretty much it. Let me know if you have any questions about this though.